Testing, testing, testing. Welcome, everybody. So here we go. Lesson 4.4, modeling and optimization. I will speak louder today so that my microphone can pick up my voice and to wake up Brian Smith. So we're going to start with a classic problem. Classic problem is this problem that you've probably seen many, many times, specifically in the calc book, because I told Ms. Sager last year, cover this one because we're doing it again next year. If you had me for advanced algebra trig, we did the same similar problem. Okay? The difference is, before calculus, we graphed it on our calculator and just found maxes and mins. Today, we're going to find the derivative, set it equal to 0, and that's how we find our maxes and mins. But other than that, it's the same problem. So when this becomes very hard for you, remember, you've done this 2 years in a row. So you have 40 feet of fence to enclose a rectangular garden along the side of a barn. What is the maximum area you can enclose? Draw a picture. Draw a picture of what's happening.
A barn.
Yep, a barn, and you got a rectangular garden on the side of a barn. And we're going to try and find the maximum of the area. Now, when you look at this, I'm going to highlight some important words. I see the word maximum. That means I'm optimizing something. I'm optimizing area. Now, the hardest part of this is to try to identify formulas from your previous classes. This is a rectangle. This is area. What formula am I using? Base times height or length times width. So I think I got stuff on the next slide. Here is my barn. Okay, it's a solid barn. Picture of a barn, just rectangle barn, because it's a side. Doesn't matter. This is my fenced-in area. Okay, now here's the weird part, and this is the part that's going to be hard for some of you. You have 40 feet of fencing. That means here, plus here, plus here can only be 40. It can only be 40. So I'd probably start with this, length and a width. And I would say this, if I add these two lengths together, length plus length, and I add it to this width, I know that it has to be a resulting number of 40. Okay? So now, the problem with optimization is this, maximizing stuff. You can't have 2 or 3 letters. So when you're trying to do area equals length times width, and you think of the graph would look like this. This is your area, and you're trying to get the biggest area, so the biggest parabola there. What is this axis if you have 2 letters? You can't do that. You have to only have 1 letter. So that's why you think about it, you write a little equation, and you kind of combine this stuff and go 2 lengths plus a width equals 40. So I'm going to get the W alone, so I don't really have any fractions. So I minus 2 lengths, I minus 2 lengths, and I get the width equals 40 minus 2L. Now in your graphs, you very rarely see L as your axis, but you could. So that's why I changed it to an X. Does that make sense? Okay, we good? Okay. So now, whenever you do an optimization problem, what you do is you write your function. If you're maximizing area, you must write an area function. This is your old area function. Write your new area function. Go. Area of a rectangle, length times width, length times width. Look at what I have there. Do length times width. And everybody, A equals something. Okay? What do you do after you get your area formula? If you're trying to maximize. Solve.
Plug in your answer for the W into the original.
Maybe, not yet. What'd you say?
Graph it.
Why do you have to take the derivative? To find maximums and minimums, you have to take a derivative. So this is kind of like, I kind of would be able to do the answer pretty easily. I think I could guess and check and figure it out. I think I can look on a graph and figure it out. However, you have to So the only way to get maximums right here is find the slope of the tangent line, have it equal to 0. So everybody, write your function, take its derivative, set it equal to 0, solve. Go. And by the way, if you needed that function, here it is. Length times width. Please watch the way you write things. After you find its derivative, and I distributed so I didn't have to do the product rule. You guys do that? And after you find the derivative, write it as a prime. The readers will want to know when you change from a function to a derivative. Okay, did you label it as a prime? Did you set it equal to 0? Now solve. How'd you do? Okay, now here's where this section becomes a little bit harder of a section. Okay, because here's what I'd like you to think about whenever you do optimization. I'd like you to think about the graph. What is this? This is area. What is this? This is x, which kind of means the length or the width, however you want to do it. It's this side. This is a side of x. So if I get an answer for x, it means it's the length of this side right here on my rectangle. So what I'm trying to do here is I'm trying to get a maximum area. So I'm trying to get the area that's the biggest. So this says here, right here, there must be a local minimum here since the endpoints are minimums. How do you know the endpoints are minimums? Yeah, but how do you know it's this parabola and not this parabola? Sure. And that's another answer. There's two logical answers. Think about it. Let's say your x value was 0. You had no length. If you had no length, what's your area? 0. So if you had no length, you had no area. And then if you kept extending this all the way down and made that x very astronomically large, where you traveled down there, then because you only have 40 meters of fencing, these sides squish in too, and then your width will be 0, if you can kind of think of that. So that should be 0 too. So I know I have this. If I didn't know I had this, or if I had a function that looked like this, you might have to check all of your minimums and maximums. In this case, you don't, because it's a quadratic. So I took the derivative, I set it equal to 0, therefore that gives me the maximum. Answer the question now. Don't forget the question. Kristen, what's my answer? 200. How'd you get that? Length times width. And if you kind of look at it, this is 10. And what's this side? 10, that's 20, 40 minus 20 is 20. And then you did area, which is 20 times 10, which is 200. What is the maximum area you can enclose? Area equals 200 what? Squared. Boy, this problem seems pretty easy, doesn't it? Yeah, they are. I don't know if I have the last slide here. And then don't forget to label your answers. And here's the number one mistake I see on problems is that people don't do answer the question. People are very happy by getting 10 and they're done. They didn't realize that the area is the answer to the question. And I think I got one more slide here. The answer to the question is 200 square feet. Okay? Everybody got it? Okay. I think I'm going to stop recording for now.